Today, really, I want to kind of ask this question about why we're not using reinforcement learning for robotic manipulation, and I guess specifically for image-based robotic manipulation. So this work was done when I was an intern at Ocado Technology. So I collaborated with Anson and James, who were at the company at that time. Um, so the reason why I'm asking this question is because it seems like nowadays, and a lot of these conferences related to robot learning, most of these methods are imitation learning. And it seems like imitation learning is taking over. So why do I say this? Recently, there are OpenVLA, there's RTX, there's Aloha, diffusion policies, Okta, and many more, many more. You can enumerate them for a long time. Um, it's not really a complaint because I think it makes sense. At least even based on my experience, imitation learning is very reproducible, especially with behavioral cloning. The setup is supervised learning. We have good guarantees for that situation. Um, just easy. But I think when everyone's focusing on this, we kind of miss the whole original limitation of what imitation learning can have, at least in the standard sense. So if we consider the standard imitation learning pipeline, we always start with having an expert that collects data in the environment. So it collects state action pairs and store this into an offline buffer D. And using this offline buffer, we'll run some offline imitation learning algorithm, like behavioral cloning. That's the most classic. Then we'll get a policy pi, and we just deploy this pi and let it continually interact with the world, and we just call it a day, right? This is standard pipeline for imitation learning, and it seems fine, just fine. But in, let's say, production setting where it's really hard to get a demonstrator, like a human demonstrator, for example, or if we can only develop hand scripted policies, then we really need to ask this question of, do you really have an expert, or are you really the expert for the task that you have? And this is pretty much a criticism of imitation learning as a paradigm, because we really need to assume we have some optimality on the experts. And this is where, reinforcement learning kind of comes in to kind of save the world, So why do I say this? So again, this is like a pipeline very similar to the previous one, but with two modifications. First modification is that as we have the demonstrator, because now I no longer assume expert, collect the data, instead of just having the state action pairs, we also get a reward from the environment. So this can be done quite easily in production setting, right? You can just have some scripts running for a day, you collect that data, and then you can annotate offline. You store this data, and you train a policy pi similarly as before, and you deploy it to the world and let it continue running. But now this time when we run continually on the deployment, on deployment, we also continually collect the data, including the reward function, and aggregate into this replay buffer. And we continue, and with this aggregation, we again update the policy. So now there's this cycle on the right where you can continually improve over time. And I will call this like autonomous improvement. And this really is the part where it allows reinforcement learning to to get an edge over imitation learning. So of course you can say, oh, inverse reinforcement learning is a thing. You can still continually interact online. But I just want to emphasize that in most of these situations, we're still trying to minimize some divergence between your learner policy and your demonstrator. So there's still limitation with regards to those imitation learning assumptions. So here are two examples where reinforcement learning appear to be better than even the top player or the top competitor in their corresponding area. So on the left, we have drone racing from, I think, a lab at Zurich. And on the right, we have Sony that developed an RL algorithm that can do racing and Gran Turismo. So in both of these cases, the RL agents are able to outperform, if not comparable with the world champion. And there are many more examples, right? DeepMind had AlphaGo, AlphaStar. OpenAI had Doda. All those situations are using reinforcement learning, and they end up being better than the best, well, one of the few best people that there are in those domains. So we're done. This is it, right? RL is the best. At least I wish that's the case. Something that we often overlook with these great application is how much engineering they put into getting these algorithms working. So in the previous two examples, as well as the AlphaGo, AlphaStar, those examples, they all involve a component of simulation. And specifically for the drone situation, they train the RL policy, from what I remember, they train the RL policy and the simulation, and they apply them to real. So this allows you to kind of alleviate exploring in the real life. So the question now is, what happens if we can only do real life exploration? And this kind of ties into the Alberta type of thinking of the world as a big world, and it's really difficult to simulate everything that you can have. So here's just an example of running soft actor critic in real life. So in the video on the right, what the agent is trying to do is to pick up an item in the bin. You can't really see the item, unfortunately, but it's a rice bag. So the arm will need to go down to the bin, pick up and get a vacuum seal on the item, and then lift it up, and that's it. So I would say have fun exploring, right? Because, well, what's the probability of getting a grasp? The probability of that will be you performing correct actions for t time steps consecutively. So that probability is actually quite low. If you only make 10% mistake, or even 1% of the time your policy make a mistake, there's an exponential decay on the probability of getting a success rate, a success grasp. So this is very, very unlikely. So one of the first false promises of reinforcement learning is, it's very common, which is exploration is very difficult, especially in the robotic setting. This is very, very hard. We need to worry about smashing the arm into the wall, or breaking the item, or breaking the arm itself, or hitting people, right? All those things are really pragmatic considerations when we want to apply RL in real life. So of course, the whole paradigm started with, we have some demonstrations. So let's just replace this exploration with some reasonable demonstrations. So it's not like we never see positive reward. So let's assume we have some positive examples. Is there other problems? And I would claim that there is another problem. And that comes from the offline phase. The motivation comes from the offline phase. So I have this 2D research task in real life where I collected 50 demonstrations and state-based observation. So in this case, what happens is you have your proprioceptive information, so the TCP pose on the arm, and you have an XY location corresponding to where the arm should go towards. So in this situation, you run offline RL, like conservative Q-learning. So everything's fine. So if you look at the plot over here, the gray is the demonstration. So on average, the demonstration is able to get 45-ish return, which is quite good. Behavioral cloning is essentially able to recover the exact same performance. And the two blue bars are offline reinforcement learning algorithm. The left one is just vanilla, nothing special. You just train using CQL. And on the right, you kind of do some extra data augmentation to add more coverage on the state action pairs. So in this case, all of the algorithm seems reasonable, even offline RL algorithm, even if it's not exactly performing as well as the demonstrator, still recovering quite well. So this is state-based observation. But the moment I get to image-based observation, these findings seem to be very, very different. So in the same 2D research environment, I only replace the target location with an image that indicates where the arm should go. So now the image corresponds to an arrow pointing to a direction with its magnitude or the length corresponds to the relative distance. So in this situation, again, demonstration is the same as the same policy. Behavioral cloning is able to recover almost exact same performance, perhaps except for one outlier. But offline RL is really, really concerning because if we look at CQL, it no longer performs reasonable at all. Actually, in fact, it never stay at the target location. It just passes by. That's why it gets some non-trivial reward. It gets some like positive reward, but it doesn't stop there. Even with data augmentation, it helps a little bit, but not too much. Like it's not as good as what we see on the left over here. So really the question now I have for reinforcement learning is behavioral cloning still works on these situations, even if you change from state-based into image-based, but RL doesn't work anymore. So I really am curious about whether or not our RL algorithms are working. And I think this kind of raised a second challenge, which are kind of brought by many people have raised this question as well, is that learning from high dimensional data is very, very difficult with reinforcement learning. And one intuition that I have from at least from these experiments is that if we look at the difference in behavioral cloning and reinforcement learning, behavioral cloning is very simple. Again, it's supervised learning. The moment you get to supervised learning, there are all these nice properties with deep neural networks. So for example, in standard classification, right? If you have overly parameterized network, then you can overtrain for a long time, then you get neural collapse and get some nice generalization properties. Perhaps behavioral cloning kind of benefits from that. But reinforcement learning, on the other hand, it's not as simple. So if we think about CQL, for example, then we have two components. We have the policy, we have the critic. As you train the critic, it relies on the information or the actions output from the policy. As you train the policy, it relies on information from the critic. So there's this cycle that or interaction between the two components that are actually moving. So this is somewhat, if you will, a continual problem, even though you have an offline learning problem. So as you can see, in this case, your behavioral cloning and your RL objective have a very different learning dynamics. And my work kind of starts from this observation of the difference in the learning dynamics. And here I want to really focus on temporal difference learning when we learn the Q function. So there are many work that looked into TD learning. I actually think Glenn's group has one paper recently on very similar topic. But here I will just refer to Kumar et al., which is the author of DR3, and Yue et al., which talks about the Q divergence based on with TD learning. They looked at TD learning. So in this case, TD learning corresponds to temporal difference. And how this is temporal difference is you have this Q theta SA, which is the current prediction at the time step. And you want to regress this prediction with a target which corresponds to the reward that I obtained immediately, plus some prediction from the following time step. And here Q bar is the target network. And essentially we want to regress Q theta towards this target so that we get zero error. And once you get zero error, supposedly your critic is going to give you some reasonable values. As usual, if we want to optimize for this objective, we perform gradient descent, right? So if we make some assumptions on the value function, let's say linearizing it, then with stochastic gradient descent, we can actually kind of quantify how one gradient descent update will influence any other value function, any other Q values. So how? So by some linear first order Taylor expansion, what you can write is the following. the first top equation is all we care about in this case. The new Q value of some state action pair of interest will equal to the old Q value before the gradient update plus this adjustment term. And this adjustment term consists of some constant, which we'll ignore for now. And we have this term, which is related to the temporal difference error. So the TD error inside the square. And some dot product between the representation of the state action pair that is being performed gradient descent on and the state action pair of interest. And here I really want everyone to focus on this inner product. What is this inner product, right? And different if you ask different people have different descriptions, right? One is the inner product you can consider as a cosine similarity. You can think of it as a generalization. You can think of it as correlation. So one way to think about this is that if we have dot product being 0 for any two different state action pairs, then essentially what we have is recovering the tabular representation of the Q function. So what this means is if I update SA, S prime A prime will not get influenced at all. So in that case, we no longer have any generalization. But when you have very high magnitude of the dot product, then influence on SA will also have a very high influence on S prime A prime. So essentially what this means is we want to have a reasonably small magnitude on the inner product of two state action pairs. We want it to be small, but not really exactly 0 because we want some generalization. On the other hand, not too big in the order of, let's say, 100,000 and so on, because now that will induce overgeneralization. So as a result, what we end up doing is introducing this regularizer, which is actually very similar to DR3, ends up being very similar. I didn't even know when I kind of worked on this. So that we just want to sample any states from your replay buffer, and you're just going to minimize the dot product or the inner product so that it gets close to 0. But you're not trying to make it only negative or only positive. You just want the magnitude to be small. And in this case, the actions are sampled in such a way that one of them is the uniform action, which kind of allows you to have more coverage. And the other action comes from your policy so that we have coverage at the same time we focus on the quantity that actually matters when it comes to critic updates. So if we kind of look at the features or the latent representation now of these neural networks, then we can see the following. So here are two plots, their top row and bottom row. Top row is the latent representation of different algorithms after the offline RL phase. The bottom row is the latent representation or the dot product of the latent representation of all these different algorithms after online RL. The first two columns corresponds to run using the regularizer to reduce the magnitude. And the last two columns corresponds to cross Q, which is I guess a somewhat new off-policy actor critic algorithm that leverages batch normalization instead of a target network to train. And you have soft actor critic, which is a very common off-policy actor critic algorithm. And we can see on the right two column, in those cases, the magnitude of the dot product is actually quite high. So in this case, the brighter the color, the higher the magnitude. And actually, if you look at bottom right, essentially, soft actor critic has very, very high magnitude on the dot product, regardless of whatever state action pairs you're comparing. So what this means is it's kind of saying that all the state action pairs are very, very similar. And in fact, I clipped this range to be 10 to the power 4 so that it's a little bit more reasonable. But otherwise, I can actually go up to the order of 6. 10 to the 6. And generally, we can see cross-Q and soft-actor critic to have somewhat higher magnitude when compared with using the regularizer, right? Of course, because we're focusing on minimizing this inner product. So they're small. So what, like, why do we care about this? So remember, if we go back to the TD learning, we can write the Q value of some state action pair to be the old Q value plus this inner product times TD error, right? So if this magnitude is large, then it's going to influence the Q value a lot. But on the other hand, if the magnitude is small, the influence is pretty small on the Q value for other state action pairs. So if we relate this Q S prime A prime as the target value that we bootstrap off of, then what this means is your Q value, that the bootstrap Q value, is no longer going to change significantly. So why is this insight important? I want to kind of recall that the whole reason why in temporal difference learning we use a target network, or not the only reason, but one of the reasons why we use it is because in previous work, we noticed that using a target network, we delay the Q value updates so that the TD learning will be less likely to diverge. And some other work has also looked into if you were to clip or have bounded activations on your critic network, then your critic will no longer diverge. So all these tricks essentially are there to make sure your TD learning doesn't diverge as quickly as possible. So what my claim here is if we can approximately orthogonalize the features, then essentially we somewhat get very close to the tabular setting, which is no longer the function approximation setting. So in that case, it's probably sufficient to alleviate Q divergence with these features. So as a result, if you use this regularizer, there's really no reason to use target network at all. So my whole purpose here is just to have this regularizer to kind of identify images that really matter, that are really similar to each other, to have high magnitude. Images that are very, very different will have very different magnitudes. Sorry, will have very, very small magnitudes. So in this case, we can just replace this target network with this regularizer, then we'll be able to kind of stabilize learning. Or at least that's the intuition of it. So if we actually do use this method, what we see is that our method is able to stabilize the Q value estimates. So here what you see are 3 plots. On the leftmost is the offline learning Q value estimates. The middle is after 100 online interaction episodes. And on the right, you have 200 online interaction episodes. In all of these cases, we just randomly sample 500 state action pairs. So these state action pairs are not necessarily optimal action. So we don't expect the return to be high for those. But you can see here, both cross-Q and soft-actor critic have very, very high values. There's interesting trends, but generally they're always overestimating or mostly overestimating, whereas our method never overestimates. Remember, 35 is around the maximum return that we should be getting in reality. And because with random state action pairs, really the Q values are not supposed to be that high. So our method seems to be able to kind of stabilize Q learning in a sense. So great, like dealing with Q divergence, you make sure that they're within the range. So what, like it doesn't really mean anything. But the nice thing about the regularizer in this case is that because you're orthogonalizing features that are very, very different, or images that are very, very different, then you can really expect that if I were to do updates on some subset of images that are very similar, it shouldn't influence other images that are not as similar. So that's the whole point. So I don't have any theory to prove those, but those are things that they're based on intuition right now. So what I want to show now is to kind of make sure this Q divergence alleviation can help with policy learning. I started off with running offline RL and RoboMimic environment. So RoboMimic environment is a suite of robotic manipulation tasks. So notably, there are three that I tested on, which is lifting the block, um, picking and placing the can into the correct location, and picking this square nut and placing it onto this pillar. So in the standard conservative Q learning, square and pick and place can are actually fairly difficult. They're unable to achieve high performance, regardless of the demonstrations. But with simplified Q, we're actually able to do better generally and actually do quite well with pick and place with one proficient human. But unfortunately, even if I'm able to kind of get these results a little bit nicer with RL, none of them are able to outperform behavioral cloning. Mostly because these these demonstrations are really, really good already. But the whole point here is just to kind of show that we're able to, this algorithm is not total random thing. It's able to help a bit.
So sorry, then maybe a quick question. Have you run your algorithm here on less optimal data from like not the expert stuff that's used for behavior cloning?
No, but I will have some results afterwards where in real life I have demonstration that are doing the task properly, but not enough for behavioral cloning to do well.
Okay, thank you.
I guess while you're on this slide though, Bryan, because I noticed on Lift PH, it seems like your simplified Q learning is doing worse than CQL.
Yeah.
Like, and that's like the same architecture and you're just changing the training algorithm. Is there any explanation for this?
So when I was looking at the learning curve, what happened was one of the seed diverged. So that explains the higher standard deviation here.
Okay.
But supposedly if that seed did, I mean, like, of course the seed does mean something, right? But it's mostly due to that divergence. And it seems like when you increase the critic network size, it's less prone to diverging. So you can see the moment I just blew up the critic, it just helps way better. So there's some like optimization part that I'm not totally sure about.
Okay. But I guess kind of with the wider critic results, is that like the same size as the network using the CQL results, or is the CQL model the same as the simplified, like the third column?
Oh yeah, second column and third column share exactly the same hyperparameters and network. And then simplified Q will remove the target network and replace it with the regularizer that I introduced.
Oh, so it's like the wider network using the same parameters as if you had a target network, I guess. Does it make sense what I'm asking? Like, are the number of parameters compared to like CQL and the wider network similar if we also include like the parameters you need for having a separate target network?
Right. So in that case, I would say so CQ and simplified Q, they have two hidden layers, one with like 300 neurons and the other with 400. This wider is always it's also with two layers, and both of them have like 2000 neurons. So I guess it'll still be a little bit more than if you were to include the target network.
Okay.
Yeah.
Thanks.
And then, sorry, quick question. The wider network on the right, that's just, are the hidden layers wider, or is also the like encoded representation you've been looking at also wider?
The hidden layers are all wider, yeah.
Okay, so then not the end of the network where you're computing this regularizer. That's the same size.
Oh, so the regularizer that the latent representation is the regularizer is operated on the second last layer output. So in this case, it will be blown up to 2000 as well. Yeah, for comparing the regularization.
Okay.
Yeah. So this is like pure simulation, and also it's still using low dimensional data. These are not image based. If it's image based, actually none of the I wasn't really able to run the experiment for long, but so far the learning curve after I think 200 like few thousand gradient steps, it's not working for both CQ and simplified Q. Um, So what really mattered at the end for us, at least during my internship, is actually getting reinforcement learning working in real life. So I spent most of my time just getting this working in real life. Um, Here we focus on this offline to online setting where we are given 50 demonstrations and we're going to pre-train it using some using the offline RL algorithm, and we're going to continually run the policy for a few hundred episodes and just continually train. This environment that we have is a grasping environment. So we have a UR10 arm. It has a camera on the gripper, which will give us a 64 by 64 RGB image. And along with the proprioception information, including the TCP pose and velocity, as well as the vacuum suction reading. Here, the action space is TCP linear and angular velocity control. So that's 6 dimension, plus the vacuum on-off action, which adds up to 7 dimension. And here, the action frequency is 10 hertz. And this is a sparse reward setting where you only get reward when the item is picked up and lifted up high and +0 otherwise. And here, the grasping attempt lasts 6 seconds, and it's fixed at 6 seconds unless there's a p-stop. So if you're able to grasp the item as quickly as possible and then you hold it high up for a long time, then that's when you maximize the reward. So the reason why we have this setup is because once we grasp the item, we also want to make sure that the policy is able to kind of grasp it in a stable way so that when we actually end up moving it from one location to another location, it doesn't drop in the middle. So the bottom here are just some of the example observation images from the camera. So the RGB got flipped to BGR because of OpenCV, but these are supposed to be orange bags. So this is what it sees. So again, in the offline setting, we have 50 successful demonstrations. They're by no means optimal, but they just pick up the item. Here we can see behavioral cloning is unable to, get that extremely good result that we saw 2 slides ago. Here we only get around at most 40% success rate. Simplified Q, unfortunately, is unable to beat behavioral cloning, but it's still able to get some non-trivial amount of success rate, and this is around 30%. And finally, we have DR3, which is the paper from Kumar et al. That introduces a very similar regularizer, but still has the target network. Here, DR3 is still able to achieve non-trivial success rate, but somewhat lower than ours in this case. And I also tested with soft actor critic, cross Q, and soft actor critic with layer norm, which is known to supposed to mitigate Q divergence. So in all those cases, they got 0 success rate. That's why I didn't really like plot them here. But this is a good sign already because for both simplified Q and DR3, they have very similar implicit regularization technique. So perhaps really is suggesting that the learning dynamics for temporal difference can be somehow, well, not fixed, but can be assisted with these type of regularizer that focus on the representation, like how decoupled these representations are. So now with these policies, I deployed it onto this robot and let it run for 200 episodes. So I actually ran all the algorithms that I tested for 3 seeds. I'll just start with cross-Q, soft actor critic, and layer norm, which is LN. None of them were able to achieve any grasp success over the 200 episodes, nor after offline training. But they still have very different behavior, which I'll show later. DR3 and simplified Q are able to continually learn. And you can see simplified Q specifically is able to actually get up to around 75% success rate on average. And that's a way tighter confidence interval compared to DR3. And for a roboticist who cares about how often we actually break the arm, the good thing about our method is that as we train and get better success rate, the p-stop rate also decreases. And again, this confidence interval is very, very narrow compared to the other ones. So I did mention cross-Q and soft actor critic have very different behaviors. So really what I want to show now is behaviorally, if we were to kind of look at the XYZ linear velocity of these policies, what we end up seeing is cross-Q started doing bang-bang actions for all XYZ. For a soft actor critic, it's even worse in the sense that it goes only towards one direction and just stays there. So it reaches like really far away from the bin. You can see that the z-axis is positive, so it actually goes away from the bin. And whereas our method, simplified Q, you can see bang-bang behavior on the z-axis, so it goes down as quickly as possible and lifts as quickly as possible. But for the XY, the actions are a little bit more fine-grained. It's actually trying to aim towards where the item is. So here are some videos of the simplified Q immediately after offline RL, which is the video on the left. And on the right, we have offline to online reinforcement learning. On the left, you can see immediately it just got a p-stop. But you can see in general, simplified Q is able to kind of pick the item in a quite meaningful way. Let me just speed it up a bit.
Can you actually go back to your last slide for a second?
Oh yeah, sure.
I'm just wondering about, like you're saying that you don't get as much bang control. I at least maybe missed the connection for like how the objective you're using results in less bang control.
So there's no direct cause from our objective that like in our learning that makes it less bang or more bang. I think it's just interesting. It's just an observation we had at the end that both soft actor critic and cross-Q ended up exhibiting, weird behavior in terms of having bang actions, whereas ours and DR3 actually seem to be a little bit less bang in terms of its behaviors. In terms of getting bang behavior on the z-axis, this somewhat makes sense because you want to go into the bin as quickly as possible, and you want to retract from the bin as quickly as possible once you get a pick. So that part would explain, but XY is just more like a precision type of control that we want.
Okay, thank you.
Yeah. Yeah, so we can see essentially simplified Q is actually able to just focus on where the item is most of the time and just pick it up as quickly as possible. And what's more is we actually froze the RL agent after online training and deployed it on different items. So we tried it on a blue rice bag, which is just in terms of color different, and a totally different item, which is the cookie can, as well as enumerating different numbers of objects in the bin. So we tried 3 items in the bin, and finally we also tried changing the lighting condition. In terms of dealing with similar items like a blue rice bag, in this case, the policy is still able to do quite reasonably well. But the moment you change the physical property of the item, let's say a cookie can, where it's like very, very rigid and the height is very different, then you can see on the right, the robot most of the time is unable to deal with this unseen height. For out of distribution actions, items, if you include more items, like 3 of them, then the policy performs just very, very suboptimally. Whereas if you still have multiple items, but similar item, orange bags and a mixture of orange and blue, you're still fine. So this is somewhat promising because what we expected originally with this RL algorithm is that I would just do very well on the orange bag, but not on unseen items. So this is somewhat nice because now I can actually change my toad with different items and still run the same RL algorithm and just let it continually learn over time. So this is pretty much like the end of like the results. I have some thoughts about this line of work. I think there's still a lot of questions of what in terms of what I did. For example, the behavioral cloning versus RL objectives is still not clear, like what's actually making one easier than the other than the standard sample complexity stuff. Second question that's been bothering me is whether or not Q divergence really matters, because it's not like soft actor critic never works in general when Q divergence happens. So what's really the necessary condition for policy to learn properly in this case? And finally, I think the method that I came up with, a lot of times it's kind of based on some intuition. There's some minor derivation that gives us that intuition, but there's no formal proof saying that, there's a good convergence, it's like sublinear convergence bound and so on. So that's one part. The other part that I really got me thinking was, do we really need that much demonstration from, let's say, RTX, OpenVLA, all those like extremely large data set? We only use 50 demonstrations and maybe a few hundred more online episodes to collect data. I think for one task, it doesn't make sense to have that much, but perhaps if we go for data diversity, this makes sense. But at the same time, I'm kind of curious whether or not we're actually going for it right now. That's another question that I'm having trouble kind of thinking about. And finally, I totally cheated by using demonstrations and ignored exploration. This is still a very, very big problem of running reinforcement learning in real life. How do we run safe exploration? Are we forced to use simulation to make sure we're fine? Can we do dynamic collision scene, all those, more pragmatic type of techniques, but actually going to be very important to get RL to work in real life? And finally, coming from Alberta, I want to make RL great again. 10 years ago, a lot of robotics labs use RL, like OpenAI and DeepMind. Now it's not so much. Everyone started using imitation learning. So I hope everyone gets excited by RL again and start using it. And that's pretty much it for my presentation. And I'm open for any questions.
I mean, I guess there was at least one I was wondering about, even when you're going over the theory. I mean, there's kind of a general question about whether or not when we're doing RL, we should also be learning perception for RL from scratch. Have you thought about that? Like, for example, maybe looking at what you were showing for some of the original work, or maybe you use some pre-trained chunk of a network that handles the perception part of learning, and then you kind of get two different encodings to maybe look at to control the magnitude of their dot product?
Yeah, that's a very, very good question. Actually, I probably spent 1 or 2 months just thinking about that problem. And I think in short, my final thought for that period of time was that any type of self-supervised learning objective that we use for pre-training an image encoder will bound to lose information. And the moment we lose information, we're unable to, use it for any type of task. So for example, policy and the queue function, they might require very different representation. So one way to think about this is the policy, if you want to just be able to represent the optimal policy, then behavioral cloning is actually a very good objective because um, essentially you can get invariance on the actions so that all the states that yield the same action should be grouped together. But the moment you have this representation and you put it on Q learning, Q learning, that doesn't work anymore, right? Because even if you have a state that has the same action, their Q values can be totally different. So we're able to kind of leverage invariance in that case, but at the same time we lose some information. This can apply for using forward dynamic modeling, inverse dynamic modeling, clip, and so on. One thing that I found to be the most consistent and the most helpful is using successor representation. So there's a paper from Sergey Levine's group on using successor representation and representing it using the Hilbert space. So the paper is called HILP. That representation seems to be very, very good because it only captures temporal distance in the latent space, but it doesn't really throw away information about like you're not aliasing two different images in that case. And I actually did experiments where I used pre-trained model using that objective and versus training end to end. And it seems like, in terms of like short horizon, training with very little number of steps, it doesn't really matter too much whether or not you do end to end or pre-trained. But at least for one seed that I was able to run for a long time, this is 800 episodes, so that's like more than a day. I was able to see that end to end actually achieves near 95% success rate, whereas Help was unable to do so. But of course, this is just one seed, so I'm not going to claim that it's never going to do 90%. But the benefit of pre-training sometimes is not only on having a good representation already, but also speeding up your training time, right? End to end, you also need to do gradient updates on your perception module, which can most usually be way bigger than your policy module. So in this case, training end to end took like 40 seconds for 60 gradient steps, whereas training with the pre-trained is taking only like 3 times less, like 15 seconds at most. So there is different benefits based on what you're able to tolerate in that case.
Okay, thank you.
Thanks.
I guess the question I was thinking about, the results you were showing us, maybe you said it, I just completely missed it, but for the online experiments you did from the representations, did you also compare with using like the behavior cloning pre-trained policy? As part of the like online training as one of the comparisons, or was it all just the RL algorithms?
So are you saying like for behavioral cloning, you train behavioral cloning first and then you run RL algorithm online using that?
Yes. Yeah.
Right. Yeah, so I've actually tried that, but not in this environment. I tried it in a simulation back then. What I found a lot of times was once you do behavioral cloning and then you run RL algorithm on top of that behavioral clone policy, is that especially with off policy algorithms, the parameters of the policy just gets destroyed almost immediately. So it will pretty much undo what it has learned. And the intuition I had there was essentially the mismatch in the behavioral cloning objective and the policy gradient objective. If we think about it naively speaking, behavioral cloning in a 2D space, let's say, behavioral cloning might be in the very negative x on a very negative x quadrant, whereas the optimal policy gradient objective is at the very positive x quadrant. So in that case, you're kind of like, in order to go from behavioral cloning to the true optimal policy gradient, you need to undo everything that you did in behavioral cloning. That's one of the intuition I had. I also tried PPO. It also seemed to destroy it at the end. So I didn't really try it on this experiment afterwards.
I guess, I don't know, a follow-up question that comes to my mind then is, I don't know, what's your opinion on, say, like, we do offline conservative Q learning and then use that representation with SAC or a different online algorithm? Would that not erase all the previous information as much compared to, say, using behavior cloning to do the pre-training?
Yeah, I think actually there are a few papers that start with conservative Q learning and then just use SAC afterwards or some other online RL algorithm. My thought there is, to be honest, I've never tried just removing the conservative Q term when I transfer it to online. So I'm not totally sure how that would play out. I don't really have a good answer for that, to be honest. But one reason why you want to do that, if you pre-train with, let's say, CQL, is that because CQL, you're pushing values that are unseen to have very, very low values, right? So you remove the policy from having the incentive to explore. So in that case, that's actually undesirable if your demonstrations is very, very suboptimal. So that might be one reason why you want to remove it. But I don't have a good answer for like when to do it and when not to do it.
Yeah, no worries.
Maybe a quick question. Just curious if you can answer this one. So the RL policy that you've been training for grabbing chip bags, does that happen to be faster than we'll call it robotics policy that, Ocado is using for grabbing chip bags in its system now?
So I don't really know, to be honest. In the case where they use their standard like scripted policy, the arm is actually able to run as quickly as possible. Of course, at the cost of like if it misestimate things, so it just pre-stop in a very poor way. So it's unable to kind of reach that velocity. But what I was able to do was, if I increase the velocity limit on the arm for the RL agent after demonstration was collected, then this RL agent can actually go beyond what the demonstration was able to get and get higher velocity motion. I don't have the result here, but internally I did that and showed, and they were pretty surprised by that too. But still some steps before getting to using the full velocity of the arm.
Okay, great. Other questions? Right. Thank Bryan for his talk again and for being able to share his thoughts. Thank you.
Thanks.
And I guess that's it for today. Take care.
Thanks again, Bryan. Good to see you.
Thanks, Michael. Thanks, Glenn. Thanks, everyone. See ya.
Thank you.